we will study a new concept called stationary distribution for a Markov chain. So let us take a look of the Markov chain here. So we let Pt to be equal to the vector of P0t, P1t, and P2t, where Pjt represents the probability that the chain is at state j at time t. Now suppose that someone tells you that Pt at time t is equal to 0.4, 0.2, and 0.4, which means that at time t, there is 0.4 chance that we are at state 0, 0.2 chance that we are at state 1, and 0.4 chance that we are at state 2. Then what will be the probability distribution when we are talking about time t plus 1? Now, previously we have mentioned that we can easily obtain Pt plus 1 based on Pt using this Markov chain. The idea here is, in order to find out what is Pt plus 1, let's analyze what is the chance for each state at that time. So for instance, for P0, if we look at P0, the chance that we are going to be at this state at time t plus 1, it is only happening when we were at this state at time t. So when the previous state is here, then it is possible that we are going to be at here. Now because Pt for the state 2 is 0.4, so 0.4 chance here previously, so in the next one, then it is going to be 0.4 here, because 0.4 times 1 is equal to 0.4. So we get that P0 at time t plus 1 is equal to 0.4. And similarly for P1, then we can do the measurement like this. If we look at state 1, there is only one incoming arrow. It is from state 0. Because we have 0.4 chance that we are at state 0 previously, so 0.4 multiplied by 0.5, we get the chance that we are at state 1 in the next state, in the next step. So it is going to be 0.2 now. And finally, because there are just 3 states, so we have already computed P0 is 0.4, P1 is 0.2. So in that case, P2 will be equal to 1 minus these 2 terms, which is equal to 0.4. And suddenly, we will realize that if Pt is 0.4, 0.2, 0.4, then we will also have Pt plus 1 to be the same, 0.4, 0.2, 0.4. And what does that mean? It means that at t plus 2, you will also have this distribution. And this distribution stays forever once we have Pt equal to this value. So in that case, this probability distribution is called a stationary distribution, because once we have arrived at this distribution, then this distribution will stay forever for all the times afterwards. Now, we may wonder whether a Markov chain can have more than one stationary distribution. Now the answer here is yes, it can have more than one stationary distribution. Just take a look of this gambler's ruin Markov chain as an example. So 1, 0, 0, 0, 0, 0 is a possible stationary distribution, because once we have arrived at this distribution, it stays forever. And similarly, 0, 0, 0, 0, 0, 1, it is also another stationary distribution. And of course, L1 over L1 plus L2, and then L2 over L1 plus L2, these two cases, so if we have the probability for these probabilities here, and then 0 in the intermediate, this is also another stationary distribution. So in general, a Markov chain could have more than one stationary distribution. And how about the opposite? Is it possible that for a Markov chain, it does not have any stationary distribution? The answer is yes. Now, although we are studying finite Markov chain in these lectures, but then there are actually infinite Markov chains. So in this case, for instance, this is a Markov chain with infinite number of states. And then with state 0, at the next time, it will all go to state 1. If you are at state 1, at the next time, it will go to state 2, and so on and so forth with certainty. So in that case, we can easily see that for such a Markov chain, there is no stationary distribution. So one question here is that, are there any special Markov chains where there is one and only one stationary distribution? And now we are going to introduce some special Markov chains, and we show that under certain conditions, then we can claim that the Markov chain will have a unique stationary distribution. The first special property that a Markov chain can have is called irreducible. So a Markov chain is irreducible if every state can reach every other state, including itself. In other words, the corresponding transition graph, the directed graph representation of the Markov chain, is strongly connected. So we have some examples here. So on the left-hand side, this was the Markov chain that we were studying so far. So we will see that from state 0, it can go to state 1. From state 0, it can go to state 2. And from state 0, it can also go back to state 0. In fact, we can see that there is a cycle here. Because of this cycle, directed cycle, we see that every state can reach every other state. So this is the case for a irreducible Markov chain. And if you look at this one, then you see that for state 0, there is actually no incoming arrow. So in that case, what does that mean? So no states can reach state 0. So in such a case, it violates the condition that every state can reach every state. So in this case, this is not irreducible. Okay, another property that a Markov chain could have related to the periodicity of the states. So first of all, let us define that a Markov chain is periodic if for some state j, whenever we want to go back to itself, it always takes some multiple of d to move from j back to itself. So in other words, if at time t we are at state j, then the probability of x is equal to j at time t plus s if and only if d divides s. So if this is the case, then the Markov chain is called periodic. So if one of the states or all of the states, whatever, so if any one of the states has such a property, then this is a periodic Markov chain. Otherwise, it is aperiodic. So this is a redundant slide, sorry. And now let us see some example. So on the left-hand side, this is the Markov chain that we are studying. And then we claim that this is aperiodic. So to check whether it is aperiodic or not, we need to look at every state and show that it is not periodic. So first of all, if you look at state 0, state 0 could come back in 3 steps, right? 1, 2, 3, 3 steps. And state 0 can come back in 2 steps, 1, 2. So in such a case, state 0 can come back in 2 or 3 steps, so there is no d such that d is greater than 1 that claims that state 0 has to come back to itself with a multiple of these steps. So the GCD, the greatest common divisor of 2 steps and 3 steps, is 1. So in that case, state 0 is not periodic. For state 1 can come back to itself in 3 steps, or state 1 can come back to itself in 5 steps. 1, 2, 3, 4, 5. Now the greatest common divisor of 3 and 5 is also 1. So in that case, state 1 itself is also not periodic. And similarly for state 2 can come back in 2 steps, 1, 2, or in 3 steps, 1, 2, 3. Because the greatest common divisor of 2 and 3 is equal to 1, so state 2 itself is also not periodic. So when every state in the Markov chain is not periodic, then the whole chain is aperiodic. So this is a periodic chain. But in contrast, let us take a look at the chain here. If you look at state 1, state 1 can come back to itself in 2 steps, or in 4 steps, or in 6 steps, and so on and so forth. So every time when we come back from state 1 to itself, it has to be a multiple of 2 steps. So in that case, state 1 is periodic. It's a periodic state. And once we have a periodic state inside a Markov chain, then the whole chain is regarded as periodic. So in that case, this is a periodic Markov chain. Okay, now we have the following theorem. It says that when the Markov chain is finite, irreducible, and aperiodic, so these are some things that is good, okay, then a stationary distribution for this Markov chain exists. Let's call it pi. And such a stationary distribution will be unique as well. So there is one and only one stationary distribution. And moreover, for a particular state J, the expected number of steps to move from J and then back to itself, okay, so we start from state J, we walk along, the first time we can come back to itself is the number of steps to move from J back to itself. And the expected value of this number is equal to 1 divided by pi j. Pi j is the probability that we are at state j in the stationary distribution. So this is quite intuitive if you believe that the stationary distribution exists. It is because if we are at state j, if we walk along many times, then we will see that forever, okay, then we will see that a proportion of pi j of these states will be state j, because the stationary distribution says that there is pi j chance that we will be at state j. Because a proportion of pi j will be of state j, so the expected number of steps from j back to itself, which is the distance between the two consecutive occurrences of state j, will be equal to 1 over pi j. So this is somehow quite intuitive. But the proof of this theorem is out of the scope of this course, so we are going to omit this one. Okay, so that's all about the stationary distribution. So for the next part, we will talk about random walk in the next part. Thank you.